Now it's my pleasure to introduce my co-chair for another talk about Schrödinger, this time Schrödinger cat, a proposed NASA PRISM investigation of the vent and the permanently shadowed regions that are in the basin.
Thank you. So this is a failed NASA PRISM proposal, although we actually felt that based on the reviews we received that it got pretty close. It is my pleasure to present the work of a large team of people. The organizations represented are the SETI Institute, where I'm headquartered, along with Doug Caldwell, who would have been our project manager. Ceres Robotics for the little rover device that would have deployed our 3 instruments. The 3 instruments would have come one from Ceres Robotics, the 2 others from NASA Ames. We also have researchers from NASA Glenn, JPL, Johns Hopkins, APL, Carnegie Mellon University, the Lunar and Planetary Institute, Planetary Science Institute, Western Carolina University, and Max Planck Institute for Solar System Research. So Schrödinger Basin, I don't need to introduce that again to you, but the key thing to note is that, of course, it's straddling here the outer zone of the South Pole Aitken Basin, and being one of the youngest impact basins, Schrödinger Basin, it likely has exposed in its surface materials, materials that would have come from the upper mantle of the moon via the South Pole Aitken Basin, which preceded it. The basin itself has many features, as we've seen this morning, but the mission that we were proposing, the deployment of our 3 instruments, it's a mobile instrument suite that we proposed, would have gone and focused on the Pyroclastic deposit, also known as the dark mantle unit of Caroline, in this Schrödinger Basin. So the scale bar is shown here at lower left. It's 20 kilometers. So this is a large, massive Pyroclastic deposit on the floor of Schrödinger Basin. This is a mosaic of the Schrödinger Pyroclastic deposit, showing you in more detail the Schrödinger vent, which we acronym as SV in the rest of our talk here. The Pyroclastic deposit is about 415 meters tall, rising above the floor of the Schrödinger Basin. It's about 35 kilometers wide, and according to Caroline, it's now 3.7 billion years old. Before that, it was estimated at ranging from 1 billion or so, at least Copernican in age from Shoemaker, to maybe 3.1, 3.2 by MEST. So this is a closer up of the Schrödinger vent. North is now to the lower right. And there are a number of interesting features about this vent. One is that there's actually a relatively shallow ramp that is very inviting in the southern side of it. So at the top of the image, if you are at the sort of the crest of the vent on top of the Schrödinger of the Pyroclastic deposit, you have a gentle ramp taking you down into this vent. The maximum slopes of order 17 degrees, which are even less than what the lunar rover drove up and down on Apollo 17, for example. Inside this vent, there is a small impact structure. The largest, there are actually several impact structures, but the largest one is a relatively small one. It's about 200 meters across, and that's a crater that we named the De Broglie crater, sort of provisionally. And of interest as well are these high albedo outcrops, which are found at sort of mid-height, mid-elevation inside the vent. And the vent itself presents a permanently shadowed region in its northern end, which is of course very exciting, because now we are looking at the possibility that it be cold trapping not only exogenous volatiles, but potentially endogenous volatiles as well, associated with the volcanic activity at this place. Now, we don't think that there would be exposed volatiles at the surface because of the indirect lighting from the rest of the vent onto the PSR. So the PSR might not be completely dark and therefore not extremely cold as the ones at the poles. But At the same time, the subsurface we would expect might be able to hold a concentration of volatiles in the PSR. So this is a profile of, well, this is a perspective view, but in the insert set, you see a profile, A to B, that's shown at the bottom of the image. What you see here is that the pyroclastic deposit rises above the floor of Schrödinger Basin, drops down again towards the southeast, and the vent itself is relatively deep because it dips below the level of the floor of the Schrödinger Basin. And what's interesting is that the outcrops that I was pointing out earlier, according to one of our co-investigators, David Kring, the outcrops could be either a carapace of volcanic melt exposed here on the sides of the vent. It could be potentially distal impact ejecta from nearby highlands. But more likely and very intriguingly, it could be exposed bedrock from the Schrödinger Basin floor because of the elevation at which it appears, and also some hints of layering that we see in these outcrops. And below these outcrops, there are rock falls that would allow you to examine up close samples that presumably would have come from these outcrops. And so the mission that we were proposing was to go investigate this pyroclastic vent, but also, and of course, its PSRs and volatiles, but also the potentially extremely fresh Schrödinger Basin floor material that are still preserved and might have rolled down from these outcrops. So the hypotheses we were going to test, here's a subset of them, that the pyroclastics at Schrödinger vent are compositionally distinct from the Apollo 15 and 17 glasses, which would imply that there's substantial lunar crustolateral compositional heterogeneities. The PSRs, large and small, I just mentioned the large one, but even the Breuil crater has a small PSR. These PSRs at the Schrödinger vent are associated with volatile concentrations, once again, not at the surface, but presumably in the shallow underground. That the volatiles would include both exogenous and endogenous volatiles. That otherwise, at least 100 ppms of water might be present even in sunlit areas. This is because this is a high latitude site, and we're building on the observations reported by recently by, and I forget her name, it'll come back later, the Sophia detection of water in at 400 ppm levels in Clavius crater, is what I was referring to. The high albedo outcrops in Schrödinger vent are Schrödinger Basin impact type, so that's the hypothesis we would like to test. Also, with our imaging system, we could examine electrostatic dust levitation, and that this process is active in the highly shadowed sort of landscape of this high latitude site. And regolith mechanics would also be examined to determine how humans might eventually access this location for scientific exploration, of course, but also for ASRU. So there were three objectives to our mission: characterize geologic features, characterize the composition of surface materials, characterize their mechanical properties, and how materials move. Three instruments, an imaging system on the rover, including 2 cameras on a pan and tilt platform, the NERVIS instrument, which is already on Viper. We would have reflown that same instrument spectrometer for compositional analysis, but also for temperature measurements, and a neutron spectrometer for bulk composition and hydrogen detection as well. So the event shows up as a thermal neutron anomaly that's relatively low.
1 minute.
Our instrument would have been able to identify different types of glasses. This is the statistical uncertainty that it would have presented as shown in the upper left. And here is a traverse, a notional traverse that we have put together to explore this vent. Of course, you have to work around the shifting lit side of the valley as you drive down, so that you're always in lit terrain. So this is showing us how we would have landed on the edge of the vent and driven down over the course of 8 days to the bottom of the pit. And I'll just end with some nice views that we were planning on getting had we been selected and flown. And so this is a depiction of our little rover carrying its instruments going down into De Broglie crater. All right, thank you very much. This is it.
Okay, thank you, Pascal, for the really interesting description of important things we still need to know and that we could investigate at Schrödinger using a mission. So maybe we just need to get more missions proposed for these geological things.
We should talk, Carolyn.
Definitely, definitely.